In this chapter, we will review the principles of electromagnetics. You might have taken a course in electromagnetics and vector algebra before, I suppose. So this will be only a review, just to remind you those principles that you have learned already. This is the outline of this chapter. It is divided into 5 modules. Each of these modules will be approximately 20 minutes to 30 minutes of lecture time. First, in module 1, I will consider Maxwell's equations. Maxwell's equations will be presented in the form of Faraday's law, Amperes Law, Gauss Law, and boundary conditions. We will look at the derivation of these equations. This part is very much required if you would like to know how electromagnetic fields, that is electric fields and magnetic fields, are interacting with circuits. The circuits can be in the form of parallel lines or power conductors above the ground, or it can be traces on a printed circuit board, or it can be component leads. We will consider uniform plane waves or transverse electromagnetic waves in different media. This is a special case of electromagnetic fields in which electric and magnetic field vectors are in a plane perpendicular to the direction of propagation. We will look into wave equations. We will consider intrinsic impedance of the medium, that is the ratio of electric and magnetic field perpendicular to the direction of propagation. We will look into the pure dielectric and the lossy media with finite conductivity. Especially we are interested in the behavior of metals when plane waves are falling on the metals. Then we will look into the concept of skin depth, that is how much the electric and magnetic fields can penetrate a metal or a conducting media. This section is very much important when we discuss shielding of electronic circuits using a metallic enclosures. Then we will consider transmission lines in module 3. Here also the solutions for traveling waves on transmission lines, we are actually considering quasi-TEM waves. But we are presenting the equations in terms of circuit parameters like inductance, capacitance, etc. Especially we are interested in termination in load as well as termination in another line, that is when the impedance of the transmission line are different. We also will consider transmission line impedance in front of a boundary. This part is important whenever we need to consider transient analysis of transmission lines or grounding conductors. In module 4, we will look into electric and magnetic fields from dipoles. We have cases in which component leads or tracks on a printed circuit boards are causing electromagnetic disturbances. So we need to calculate how much will be emitted from this. So we will see that any of this can be modeled as combinations of small electric dipoles and small loops. We will find the expressions for radiation field, especially the maximum radiation field. And we will also consider wave impedance. especially how wave impedance is different between electric and magnetic field when you are close to the source. Then in module 5 we will do several numerical examples. First we consider the illustration of line integral, which will come in several of the Maxwell's equations. Imagine a vector field in space all around here, F. Here the bar above F indicate that it is a vector, that is, it has not only a magnitude but a direction also. Consider a path A to B, and a small section of this path, which can be indicated as a vector dl. The direction of this path is tangential to the small section dl, and that is indicated by a unit vector, and a hat symbol is shown for unit vector. Now this vector f and the unit vector dl form an angle theta. Now if you take the dot product of these two vectors, then we get the component of this vector along the line f cos theta. Now let's see what is the meaning of the line integral indicated by a path C from A to B of the vector f. It is defined as line integral of a vector f along a path C from A to B is the summation, that is the integral of the product of the tangential components of the vector, that is f cos theta, and the differential path length dl along the path. Now you have to remember that both f and theta can vary along the path. They need not be constant. So that is why you need to have this integration or summation. Now if the path C is closed, then it is called a closed line integral, which is denoted by the integral symbol with a circle as well as a subscript C, f dot dl. So this is the closed line integral. Now let us look at the meaning of the surface integral. This is the Cartesian coordinate system, and imagine some surface, and there consider a small elemental surface area ds, and ds can be represented as a vector, and that is equal to the area of this small elemental area multiplied by the unit vector representing that area, and the unit vector is perpendicular to that small elemental area, perpendicular to that surface. Now there is a vector field f in space. Then dot product of vector f and the unit vector is f cos theta, and the surface integral of f dot ds, that is surface integral of a vector field f across a surface S, is defined as the summation or integral of the product of the vertical component of the vector to the surface f cos theta and the area of the differential surface ds. So you are multiplying the component of the vector field f along the unit vector with the small elemental area, then summing it up all along the area. We need to do this summation or integral because both f and theta can vary across the surface. If surface S is closed, it is a closed surface integral denoted by f dot ds, and with this symbol like this. Now look at Faraday's law. Here, concentrate on this illustration. you can consider it as a closed plastic bag or a balloon where only one side is open. Now this is the open side. Now there is a magnetic flux density vector field B. Now there is a electric field vector field E, electric field intensity. Now what Faraday's law is stating is that if you sum up all the component of the E field along a closed path and multiply it by the small elemental length, that is if you take the line integral of E along the closed path, then that is equal to the surface integral of the magnetic flux density vector. That is, if you look at a magnetic flux density B coming out of this small elemental area, and if you multiply the normal component of that with the elemental area, you get the net flux coming out of this elemental area. So you are summing up all those kind of fluxes coming out of the body of the plastic bag. Then you take the time derivative of that kind of flux coming out, and that is also called the EMF. So line integral of the electric field along a closed path is equal to the rate of change of total flux coming out of the area enclosed by this path. Now the direction of the induced current should be in such a way that the magnetic flux induced due to that current I induced should be opposing the change in original flux enclosed by the closed path. So this is called Lenz's law. So we are using Lenz's law in finding out in which direction the EMF should be, the polarity of EMF. Now for that, consider this diagram, a simplified diagram, where B is assumed to be increasing. Now this increasing B should be producing an EMF in such a direction such that the current produced should be producing an induced magnetic flux density or magnetic flux that is opposing this original flux. So using the right hand rule, the magnetic flux has to be in this direction. So this is opposing the original flux. So this is the correct direction. So that is how you take care of this negative sign. Now in this case, the increasing flux is in the other direction. So here, to oppose this flux, you have to have a polarity like this for the induced EMF. Then only it will produce a current in this direction, and that induced flux will be opposing this original flux. So in the modeling of the magnetic field interaction, you'll be using this principle. Now let us look at the units here. E is in volts per meter and B is in Weber per square meter. So Weber per square meter is also called Tesla. So these are the SI units. Now this is an illustration connecting the Faraday's law or magnetic field interaction with mutual inductance that you are familiar in circuit theory. Now imagine some sort of a current somewhere in space. So this current is I subscript G. So this current is inducing some flux in a closed path. Now this is an imaginary path. This path need not be made of conductors or anything, but of course if you want to measure something, you need to have a conductor here. Otherwise, even if you take an imaginary path in air, Faraday's law is true. Now in the case of a circuit in the form of a closed path, the mutual inductance M between this and this is defined as M is identical to rate of change of total enclosed flux here to rate of change of the current, that is d phi by dig. So this is the definition of mutual inductance. Now you can do some algebraic manipulation. You can do like this because this is the total derivative. So m dig equal to d phi. Now you take the time derivative on both sides. M dig by dt equal to d phi by dt. So rate of change of flux from Faraday's law, we have seen that it is just like a EMF, a source of voltage. So this is the Faraday's law. So d phi by dt can be equated to minus d by dt in surface integral of B dot ds. So you can see that how Faraday's law of magnetic field interaction can be modeled as a series voltage source if you are involving a circuit. So this phenomena of magnetic field interaction can be replaced by a voltage source. So the direction of the voltage source need to be determined by Lenz's law, as we have seen before. And this voltage source Vi is given by M dig by dt. So we have reduced the magnetic field interaction into a voltage source, series voltage source with the circuit. This you will see in the discussion of crosstalk or magnetic field interaction. Then we come to Amperes Law. So look at this picture. So here also imagine a plastic bag with one side open. Now there are several vector fields here. One is the electric flux density field, D. Then we have the free current field, J, current density field, J. So these are, some of these are entering the plastic bag and going out of it. It can be in any direction, you can imagine. If you look at this equation, here this is the line integral along this path, which is enclosing this surface S. Then this total current density and the vertical component of the current density coming out of this. So if you have current density coming out here and the small elemental area, if you multiply by that, then you get this small current coming out. So you add up all those small currents, and that is given by this. So these are the free currents, total free currents coming out of this surface S. Plus, now all the electric flux density is coming out, the vertical component of that multiplied by the small area. Actually, this is the displacement current term in the Maxwell's equation. So rate of change of d dot ds is the displacement current. ID. So H is given in amperes per meter. So the line integral of the magnetic field intensity vector H around a closed contour C, or magnetic motive force, or MMF, is equal to the sum of the total conduction current and the displacement current that penetrate the surface S bounded by the contour C. So this is Amperes law. Now look at Gauss law. Imagine a closed path. So it can be your plastic bag or balloon where the end is tied up. So you don't have any open end. It can be of any shape. So you have several magnetic flux density fields coming out of the closed path and going in again, or just going through it. You can have charges inside, and positive charges, and you can have negative charges outside. So there will be electric flux lines connecting these two charges. Now what Gauss law is stating is that total electric flux density coming out is equal to the charge contained within that closed surface. That is, you are summing up all the electric flux density lines multiplied by small elemental area, summing it up. And so it is the total electric flux coming out that is equal to the charge contained within this volume. It doesn't matter where those charges are. Sum of all those charges together will be equal to Q. So this is Gauss law. The net electric flux D through a closed surface equal to the net positive charge enclosed by the surface. Now unit of Q is in coulombs and D in coulombs per meter squared. Now instead of the electric flux density, if it is magnetic flux density, then we will see that closed surface integral of B dot ds equal to 0. That is because we don't have any magnetic monopoles. You don't have any positive magnetic pole or a negative magnetic pole. So that is why this is always identically equal to 0. Now let us look at the circuit implication of Gauss's law of electric field interaction and how we can tie it up with the mutual capacitance between two metallic bodies. Consider two bodies. One is charged to plus Q positively and other is charged to minus Q negatively. And there is a potential difference between them expressed by V subscript 1, 2. So the capacitance between them in circuit theory is defined as C12 equals rate of change of Q with respect to rate of change of V. So this is the definition of capacitance, mutual capacitance. Since it is total differential, you can do this algebraic manipulation. Then you take the time derivative on both sides. Then you will see that dq by dt is nothing but the current I. So it is like a current injection. Already you can see that. Now tie it up with Gauss law. What Gauss law states is that closed surface integral. So you can take a closed surface along this. Closed surface integral of epsilon E, which is nothing but D for a linear material, dot ds equal to Q. And take the time derivative on both sides. So this is current injection. So rate of change of field in relation to two conductors can be modeled as a current injection. So electric field interaction can be modeled as a current injection. So this electric field is created by these charges here. So look at this current source IC. IC is nothing but C12 dV by dt, rate of change of voltage. It is this one. Now, SI units, capacitance is in coulombs per volt. It comes from here, or we can call it as farads. The electric permittivity epsilon has the unit farads per meter.